Thank you so much, Pierre, and thank you for inviting me to this conference. It's always so interesting. I'm learning so much. I'm absorbing this time. So I was on the schedule. You could see I was saying something about ambient noise monitoring the crust, and I on Saturday sent an email like I actually don't do much of the crust, but. So what I wanted to modify this is this nice pictorial view from AI about what we can monitor with. Oops, is doing the setup show. I love that it does that by default. It's crazy. Nobody ever wants that. So what I wanted to talk to you today in application of ambient noise seismology is to have some kind of a quick catalog on all of the super dynamic Earth phenomena that we see in the shallow crust, earthquakes, volcanoes, glaciers, and soils. And all of that has been really supported by a super group of students and postdocs at various stages, received a lot of funding from various institutions, but really you'll see a lot of this work is done by these outstanding people, where I learned a lot from them. So what I wanted to focus the talk today was not on these ballistic waves, but rather focusing on just interpreting CODA waves. So I just wanted to be clear in what we'll be interpreting. We'll be looking at the seismic velocity, and there we measure phase lag in the late CODA of repeated seismogram from ambient noise cross correlation. And for that, we're going to measure the DT. And I also will like to introduce how we're starting to monitor attenuation as a measure of relative amplitude. That's great. And we're starting to measuring in a couple of ways. And I'm bringing this up because I know it's ultra controversial. But since we're Monday, we're going to have so many days that we can debate about it. And you can teach me how to do this better. And Quan Fu, who's a postdoc here, has a poster on the topic. So we'll be measuring intrinsic attenuation in the envelope of the single station correlation, but we also started exploring how to measure attenuation with what people call DSAR, or like it's a spectral amplitude ratio in the Fourier domain. So these will be the two measurements that we'll be making on these dynamic phenomena. And many of you, there's always skepticism on how to interpret the structure, signal, or information from these measurements versus the biases or artifacts that come from varying noise sources. And so what we can try to understand and discriminate between a noise source artifact versus a structural artifact is to maybe use strategies like beamforming, which we just saw. Florent was showing really localized directionality and a specific move out to tell you about the type of scattering, which was great for distant far-field sources. In other systems, such as volcanoes, where the noise sources are, or the tremor sources are within the array, we may choose other strategies to figure out whether or not our noise field is diffuse or whether or not we see very localized sources. And so for that, I'd like to say that we've been using extensive work from Leonard on cove size and a few other techniques. And this is our way to try to understand the ambient field that we have before we interpret it in terms of structure or noise. I don't know if this will be introduced in this week, so I just wanted to show one of the first papers on the topic from Leonard 2016, where they analyzed, it's basically using an array of stations for the same time of recording, and we can understand the distribution of the wave field by doing the covariance of these, the correlation of these wave fields. And when we do that and take this SVD is a fancy term for machine learning. I'm kidding. But it is the fundamental of a lot of our analysis. You take the SVD of the covariance matrix, and you can look at the spectral decay in the eigenmode that compose the noise. And so for that, it's a way to say, do I need many modes to represent the ambient field, or do I just need one? During coherent earthquake waveforms, you may just need one eigenmode to recompose the entire wave field. It's basically a shift and stack, right? Because they are almost aligned. You shift them, you stack them, you get the most coherent dominant signal. But maybe in ambient field, where the noise sources are more distributed, you may find that the eigendecomposition of the SVD of the covariance matrix is showing more modes are needed to represent the wave field. And so in a way, I thought I talked to Leonard about this. It was this technique was developed, by Michel, maybe you can correct me, to analyze parts of the wave field in the frequency domain that were either diffuse and therefore satisfy the conditions we need for the cross correlations to be related to the Green's function, or very focused, in which case it is an opportunity to detect new kinds of sources. But yet, don't use that for the ambient field, because you can look at the time dependence in these effects. So as I moved to the UW a couple of years ago, I had this natural playground, lots of volcanoes. They're not super active. It's not like Matt was playing with actual erupting volcanoes on a day-to-day basis. We have little puffs here and there. This is in 2004, 2005 for Mount St. Helens. And this is a very well-studied volcano. It's like the Etna of the lower 48 states. But I wanted to know if we had missed any indication of the onset of eruptions in the 2004 eruption in Mount St. Helens, because people, and especially the Cascade Volcano Observatory, rely on earthquake signal to predict, to forecast eruptions. And so I wanted to know that we've been missing signals from the ambient field that would tell us that an eruption was coming. And this is the work that's led by Manuela Kopfli, who's a grad student. And so with Manuela, our paper is going to come out in SRL. She started looking at this covariance analysis. So I renamed the y-axis, and you can tell me I'm wrong, but an idea of, sorry, for these curves that you see here, the yellow, green, and blue, actually the color bar, I call that the diffusivity power. And so what we're going to look at, you see all of these y-axis is frequency, and dark color means we need a lot of eigenmodes to reconstruct the signal. It's diffuse. And bright color here is showing actually that we have a localized source at that frequency and that time. And so this is a snapshot of the 2004 eruption over a couple of years. And the blue are these time series in the heat map, but shown as time series and stacked over frequencies. And what I can tell you is when you have this a sudden onset here, these are the times of the eruptions in 2004 when it started erupting. And you can see that it goes up, which means there's a lot of coherent sources that illuminate the wave field. And then it comes down to some static level, which is the level at which we believe the wave field is diffuse. Why I bring this is it's very important to understand and interpret the time series of either ambient noise monitoring for DV or for attenuation. And there's been a couple of studies that looked at the spectral amplitude ratio, the DSAR, especially in New Zealand. There's a couple of volcanoes on which that worked well. And so what we compared, and this is a proxy for attenuation, high values of DSAR in red means highly attenuative medium, low value means low attenuation. And what you can see, this red curve that we built over a time series of 20 years or so, is showing annual fluctuations and strong fluctuations during the time of the eruption. And so without doing any analysis on noise source distribution or localization, one might interpret this as saying there's higher attenuation, of course, it's erupting, it's dilating, and therefore it must increase the attenuation. But what we found is instead, because we were using a combination of techniques, we found that maybe outside of that eruption window, when this curve size, the ambient field is more diffuse, maybe we can trust these signals as being seasonal and very likely dominated by the subsurface hydrology. But maybe during the actual volcanic eruption, where we know that the noise field is very localized, then that we have to interpret this not as a structural effect, but rather as a source effect. Now, what we found in this study, it's really we needed to try all of these techniques to figure out what the difference between noise source and noise structure. Now, I've started doing this in my research maybe 5 to 10 years ago, and this is the first time I actually do a more rigorous job at doing this. But what was nice is really using arrays of seismometers, we were able to discern what was the information from the structure versus the noise, and we can now interpret these fluctuations with confidence in terms of structure. Now, usually you should start doing that first, but we all learn. So this trade-off is going to be potential present in all of the work I'll be showing, but we try to build confidence in interpreting this in terms of structure. Now, assuming that this is all structure, the seismic properties are affected by many phenomena: subsurface moisture, groundwater, rainfall, sea level rise, solid earth tide, geodynamic, atmospheric pressure, tectonic tremor, earthquake damage, magmatic storage, temperature, you name it. We can see now that the seismic properties are changing over all of these phenomena. That's what makes me so excited about studying it. In one way, it's fun. In the other way, it's very challenging. And we tend to model this dV on the top here as a constant plus a term from hydrologic signal, which can be load or diffusion. Thermoelastic strains that we may propagate. Maybe some earthquake signal, a step function and a logarithmic. Maybe some earth tides to this, barometric pressure, and you name it. And we have so far, I think, only described them as a linear summation of all of these terms. The issue is that you take the residuals and you still see patterns, which means to the first approximation, maybe that's correct, but we have some work to do on a better understanding a better model. What these terms may look like in trying to explain this seismic velocity is a load and the diffusion of precipitation, annual temperature, maybe some step function and logarithm milling, and maybe some trends. And many of us do that now. I think it's pretty standard. Like if we have some knowledge of the precipitation, of the intrusion of dike, this is something that we'll be always modeling, trying to explain the seismic velocity as a function of all these terms. Now there's work to be done, I think, in trying to understand why do we see residuals, why when we decompose this time series, it does not apply elsewhere. Every time we have to refit this time series for a different volcano, for a different faults. This is potentially that we are just not modeling this right. So I don't have the answer to this, but what we started doing, and Luc Hillian also started doing this, is maybe there's a way that we should discover the fundamental processes, the physical models that will better explain DV. And we did this with an engineer, Fabien Dewalt, who spent some time at the UW, where he actually looked at concrete and changed temperature and relative humidity in a very controlled sense. And then we're able to find changes in attenuation and velocities as a function of this term, temperature and relative humidity. And then he found, I was like, do some neural network or machine learning. No, he's like, no. We'll do a simple polynomial regression and find the coefficients that best fits this regression. And so what he found for DV, and we have a similar thing for attenuation, is just we do have this linear summation of temperature term, relative humidity term, but we also have some of the strong coupling between the two, which makes sense. Water and temperature should be coupled for thermal diffusivity. And so I feel like this is maybe one of the beginnings to start exploring maybe a better physical model that would explain our observation of DV. Another one that was very data-driven from Luc Hillian, I don't know if you remember that cool paper where it says, this is Nepal, lots of rainfall, huge effect on the rainfall. But there was also this 2015 earthquake, the Nepal earthquake. And so what is modeled is the effect of damage and slow recovery, so a model for permeability that is supported by damage or is informed by damage. Coupled to that, the response of the seismic velocity as a function of rainfall. And so it was saying, well, there's a time dependence in that sensitivity because of damage. And so this is the first time I really see that coupling done successfully. Another aspect of our measurements from the shallow crust is they're very shallow. Why? And this is something that Anne worked a lot on. This is one of the few plots that that she's made, and others have made too, is the idea of depth in kilometers and observe velocity or sensitivity to the actual perturbation. And no matter how we model this, a heterogeneous medium in a 3D medium, in a 2D medium, SpecFEM, other methods, a layered perturbation at depth or whatnot, what we're going to see is a complete loss of sensitivity quickly in the subsurface. And so if you measure dV that decays exponentially with depth, it is mostly due to that. Now, it could be an expression of a flower-like structure around the fault or something, but the fact is what we measure is a complete underprediction of what is actually happening. And so these are constraints. We make observation of dV. There's many factors that enters at play, and we model them, but not really well, but maybe it's coming. They're very shallow, and so we're only sensitive to the shallow part. And we need to care about the noise source and the structure effect and the trade-off between the two. So provided that you have these three ingredients and you're kind of cognizant of the biases and maybe limitations, now let's have some fun. And I'm going to show you kind of a series of applications that, provided that we did this right, would be an interesting new understanding on physical processes. So the first thing I'll take you is this tectonic effect. So I knew Laurent was giving a really good talk about this, so I didn't delve too much into this. But I wanted to show you the work we did in Parkfield, because I knew that was that would be different, because I think somebody reviewed my paper. This is Dr. Kurama Okubo's work. He was a postdoc with me in 2019 and continued working for like 3 years, COVID and all that, remotely. We tackled this another best studied fault, Parkfield, right? Monson-Hans, Parkfield, you see it. I just wanted to reproduce some of the previous work to make sure that we got this right. But the way Kurama did it, he used a local network in Parkfield. This is the San Andreas fault. It's that patch of the fault that nearly repeats, but not really. So it's an interesting area. It's got some good borehole stations with really good signal-to-noise ratio. It had one earthquake on it. It will have another one. And so it's cool. It's 2 terabytes, so it's not that much. And we have 20 plus years of data. This is the work that Kurama did extremely as a reproducible workflow. He did the work first on a machine called Frontera Attack. It's 2 terabytes, so it's pretty modest, but it's done very fast. It's in Julia, the computing language. It's reproduced because if you submit a pull request and a change on this code, it will generate a code testing on GitHub to re-cross-correlate, remove the earthquakes, recalculate the DV, and make sure everything's done correctly. I've never seen such a level of care for reproducible science that would be a GitHub code action. Really good. So that's a side note because that's software engineering, and that has nothing to do with the science. So I will show you a time series that you've probably seen many times before. This is the about 1 hertz cross correlations, average over all different stations, station pairs, single station. And this is when most seismic networks started putting their, keeping all of their continuous data early 2000. You know, there's some papers that came out in like 2003, 2004, turning all this ambient noise into signal, right? This is timed with the fact that these seismic networks started recording continuously. Before that, it was all triggered data. So it's an interesting network enabling new science. So in 2002, in Parkfield, we have the seismic velocity shown here. I think there's different methods, or I forgot how this is broken down. There's in 2003 a small earthquake nearby, so we see a drop in velocity, very modest, and recovery. This is just damage from the shaking of the earthquake. And then the Parkfield earthquake happened. And then Laurent publishes his famous paper, and that's when we get back to normal. So in the 2008 paper, velocity dropped twice, recovered, we're back to normal, all is good. Science or nature, I don't know, you did 2 at the same time. I forgot which one was when. Wu et al. 2016 revisited this work, reconfirmed again what Laurent saw, and I think they stopped right there, but they had this idea of flower-like structure with a depth frequency dependence thing. And then nobody else studied it because it's so well studied, but Kurama looked at this again, and the velocities kept going up. So that was very interesting. As we go on 2014, 2016, depending on whether or not you use stretching or NW, the other method, it's still statistically significant that the seismic velocities just keep going up. And so what we interpreted this after many years of debate in the group is that what we are trying to see, sorry for the offset, what we're trying to see is maybe a compaction, interseismic compaction, close to the faults. We have somewhat of a decay of that signal as we move away from the fault. But what we needed to explain this compaction, we are at the point where, you know, a lot of it is shear. It's just a strike-slip fault. So where will we see compression? Where we thought is we needed to infer the orientation of the fault crack and say there is compression in a given axis that can explain this observation. So it's a little bit subtle, maybe different. Florent was showing the dilatational, which is a all average over all components. But if you have an anisotropy in the cracks, the compression will be a lot more sensitive to one axis, and that would explain observations. So I think this is one of the few observation of interseismic loading, because we have 20 years of data, and because this is it's an earthquake that's going to happen, we know the earthquake cycle is also quite short. Although we may have another hint of that interseismic loading. So you could see Maline's poster, where Maline has been looking at subduction zone to 10 years time series in Cascadia, and maybe we also see that long-term trend. So maybe a second time. Co-seismically, we all know that seismic velocity drop. I am not showing the work here, but co-shaking, the velocity will drop during the shaking of the earthquake. Yehuda has done some work, Ambient Bonilla, on looking at during the shaking, we already have a reduction in velocity, and as soon as the shaking stops by 20-30%, and the velocity will heal soon after the shaking. And then after that, there's still maybe a residual of 10%, 12% of seismic velocity drop past the shaking of the earthquake, and it will take some time to recover. So this work was by Loic, who was also one of my first postdocs, looking at the Tohoku earthquake shaking, the Maisonette network that was back then dense, was 300 stations about, shallow borehole. The black dots are showing you the elevated change in velocity after the passage of the waves from Tohoku. So you can see a lot of dark dots, lots of changes. But remember that I said like we are really under predicting what these changes are. And the time series then, we're looking like, coast to the Tokyo Bay. Velocity was about constant. You see a drop here. That's rain. There's just a lot of signals from the rain. The Tohoku earthquake happened. We have at least 10% of the velocity, and then it takes a couple of weeks to recover. Or maybe sometimes it just never recovered. These recoveries close to the fault may take decades. So this is an example from Tim Clement's work, where he picked stations that were located close to earthquakes at the time of earthquakes. So these are the blue dots here. They happen to be at the end of northward propagating ruptures. They were magnitude 7 in California, broadly speaking. So these were a couple of magnitude 7. So being at the end of the northern tip of a fault that ruptured northward, you're close to the point where you would expect a lot of damage from energetic waves breaking the soil and the rock around. So looking back at these 20 years of time series, which one is this? It's the Ridgecrest earthquake. It's a recent 2019 earthquake. In this case, Tim removed the hydrological and temporal effects, and the station was on in the mid-2000. Velocity dropped by a few percent and then starts to recover. This one is very cool. Hector Mine in 1999. So it deployed the stations quite before that, right before the earthquake. And then it dropped by a few percent and is still continuing to recover. So it's taking 20 years to recover close to the fault. And then another one might be the Baja California earthquake, right south of the border, where it's still on the San Andreas fault system, where corrected for hydrological signal and temperature, you also see a very sudden drop and recovery that is still not achieved at that time. So in this context, I don't know the physical mechanism that would take that long. If I show what happened before, these are shaking-induced damage. You're far from the earthquake, and these were done by 2 weeks. And I think that's kind of typical for like shaking-induced velocity change. By 2 weeks, you're done. Yep. Oui. I think this was a residual from the groundwater, the removal of the groundwater signal we did for this particular example, because we did the estimation of the groundwater removal with a rainfall diffusion, but there was a nearby well that doesn't have the complete time series, but that did show maybe the residual right from that. Yes, that's why. No, this was the Parkville RG or the Mount St. Helens, like No, still not well instrumented. Not the case. Anyway, this was interesting to me because I don't know of these 20-year time scale recoveries. This is obviously shallow because we're doing like a couple of hertz. It's close to the fault. I'm expecting a lot of damage from the shaking, but it's a process that's taking 20 years. I'm pretty sure it's not that typical shallow dynamics for sediments. So please, if you have time, if you have thoughts, I'd love to get some ideas on, is that a fault zone process? Maybe more likely than the kind of geotechnical layer or shallow soils process. Okay, hydrological effects. Moving away from earthquakes. Jean-Marc is going to show a lot more of this, so I will just go quickly. Since 2006, we know that the velocity, changes in velocity, may be proportional to minus the groundwater level. So GWL would be groundwater level. So this is a figure from Christopher's paper. These are the blue and red. These are the positive lag, anti-causal lag DV, shown in this y-axis. And then the black curve here is the groundwater well at the Merapi volcano. They were looking probably for a volcano signal, ended up with a lot of hydrological signal. This is the story of our life in monitoring subsurface. And so what you can see is there's a direct anti-correlation between the two. And then many more papers found this in 2015, 2018, Jean-Marc's work that you'll see more. People did that on receiver function. All of these correlation or anti-correlation are just saying, provided that you remove all these temperature effects or whatnot, it turns out the velocity is proportional. The scale may be different in the y-axis, but it's proportional to that the hydrological signals. And by that I mean it can come in many forms. I mean the water table levels and pore pressure. Talking about water table, so before they were aquifers, this is water table, a few meters deep. It's not a complete review, but there's a couple of these studies. This is using DAS and a river gauge. This is Luke's work in soil moisture, so measuring 10 centimeter soil moisture, and your DV that's supposedly a lot deeper in sensitivity is still showing a strong connection. The DV is shown in black here, the moisture is shown in green. So at all scales in depth and spatially, people found this correspondence. Shujan used INSAR. We use a groundwater well proxy. Cool study in Grenoble found that with piezoelectric that you could basically map in space and time these changes in subsurface properties. Tim took that on and did a 20-year study in California where we collected northern California and all the temporary stations. This was about 200 terabytes at most. Because the southern California, and then we have the temporary arrays. Up to 200 terabytes of raw data. Some of it was already on the cloud, on the Amazon Web Services, AWS. And some of it we uploaded, and I pay for storage, and it was a huge, silly thing to do because storage on AWS is extremely expensive. But what Tim did is saying, we're going to do the single station correlation. We're not pairing anything, but we're looking at 20 years of data for these 700 stations. And so he coded this in Julia, and he only spent about a day of computing on one motor size. It's like your typical Linux, like 48 cores station. And so what he did is downsample the data and cross-code the single channel, parallelize heavily, and look at the single station measurements and comparing with other environmental processes. So we think that we're really sensitive to the shallow aquifer, or maybe the deep water table in California. It's very dry, so the water table is quite deep. And so in this case, our normal like 4 hertz frequencies seems to be sensitive to this deep water table. And over 20 years, this is the California weather. We got a bit of rain, a lot of rain. A bit of rain, less rain, fewer rains, less rain, drought, worry, boom, a little rain event. Drought, worry, boom, another rain event that resets. This was before the 2023 storms. I'm not sensing the fault. Actually, Parkfield, we didn't see a lot of hydrological signals. Well, the stations come on at different time. This is LGR. 2003. It's a different study. So LGR is the station. This is between Northern and Southern California. It's not the... Yeah, no, it's not the earthquake from Parkfield, which is interesting because... no, this is the winter 2004 to 2005. This is an atmospheric river, a couple of atmospheric rivers. So this bar here is the cumulative amount of rain that year. It's usually at that level, low level. And then you can have a couple of these storms. There was one last weekend in Seattle, that's why I'm glad to be here, that poured something like a month worth of rain in a day. These atmospheric rivers, they call the Pineapple Express, I think. They form in Hawaii, and they really funnel a lot of moisture on the west coast, and they dump a ton of rain all at once. But there are seasons where you get a lot of them, and so that accounts for multiple years' worth of rain in one winter. And these affect a lot of the seismic velocities and the groundwater level that you see here, where you have, and we have Grace and some model for it. But basically the velocity is shown here. By the way, I call this axis the Branguet axis. You've shown in your paper the flat axis minus is up. And so since then people ask, is that positive or negative? I'm like, it's for Florent. The Branguet axis. So it goes down, velocity goes down when the rain, when it gets wet and the water table goes up, and vice versa. So in that winter 2005, we have 2% of drop in velocity just due to the rain, load and diffusion of the rain. Okay, I am sure, this is when Tim defended his PhD, I am sure that we'll reset / above the levels with the 2003 events. But this is typical of California. I'll do a quick view on all of the stations that we've seen. A lot of seasonal signals from both temperature and hydrology. Long-term trends are going up for the droughts. LGR was, of course, the best station to study. Look at this signal, it's beautiful. But a lot of it is this hydrology term, and we see potentially a long-term change of a couple of percent over 20 years.
Can you say what velocities are these? Rainy wave velocities, P wave velocities?
Yeah, thank you. It's mostly shear waves, just because the CODA is mostly dominated by shear waves. Now, is it body wave or surface waves? I think that in the bedrock sites, there could be a little bit of body waves in the CODA, the single station. On the sediment side, all the basins, I think the early CODA of the single station correlation has a lot of surface waves. But that's up to debate, so we have all week to talk about that. But I feel like as soon as we have a low velocity layer, we just generate very efficiently surface waves. And so even for the single station measurement, these are mostly surface waves. Okay.
And since I already interrupted you,
Ouais.
when you say single station measurement, is this autocorrelation or cross-correlation between different components, or what is it that you do?
The latter. So this cross-correlation, and I think in this paper we only did the inter-channel cross-correlation and stacked over that. Yes. Okay, Quan-Fu's work. Quan-Fu is giving a poster about something else, but let me show you what she's been doing as well. Quan-Fu, raise your hand. You're here. So what we worked on with Quan-Fu's done a lot of work on velocity monitoring, water effects in Taiwan, and earthquake and water. You know, Taiwan has monsoon and earthquakes. When Quan-Fu came as a postdoc, we kind of wanted to recast this problem from here's our observation, and let me try to fit observation with a model from hydrology, because we're not hydrologists, temperature and whatnot. And so often we've been trying to build this linear superposition or combination. So with Quan-Fu, we're trying to now create a hydrologic proxy from DV. And this is because it seems like the groundwater hydrologists, at least in the United States, are not super interested in the idea that we could provide them proxies. So we're trying to recast the problem to make them understand, like, well, what if we actually turn this into a useful product? And so what we're trying to do now is predict the hydrology, the water table, from DV. You might say it's just a linear superposition, but it's also a mindset to change, really thinking about predicting rather than explaining the processes. And so an example of that, the hydrotherm, I kept it vague because Quanfu is working on soil moisture and water table from multiple proxies. So one example is how we predict the relative soil moisture measurements using ensemble modeling, comparing that with a NASA product. You can see the residuals have pattern, which means you're probably not modeling this right. But in some sense, we're trying to predict this, and this is, again, Quanfu's work. In the state of Utah, which also has long-term droughts and a short wet season, but you can see the predictions and the ones from the NASA products, which also is not ground truth measurement. These are proxies, so we're kind of lost in the proxy world. But until we get actual ground truthing, this is the best we can do. But it looks pretty good, I think. Measuring relative moisture. Moisture is very important for, land-atmosphere coupling in climate model, and the food. Okay, so this is very esoteric. So I've been working with Tarje. Tarje, thinks about elephant seismology and whatnot. We also work with an ecologist, Simon Jeffrey, thinking, what if we use seismology to really help us understand the health of soils in light of improving agricultural practices? So this is not Brittany, it's England. It's so different, okay? It rains a little bit less in France, barely. But we're still doing a lot of agriculture. I'm from Brittany, sorry, that's the joke. I come from this farmland. We went to England in March. It was very pleasant. It was something like 10 degrees and wet. And we deployed a DAS. This is Ethan Williams, who was John Wen's student, and Simon here, the ecologist. We deployed the DAS, surface on the soil, do not stamp on the soil. It compacts it, it will completely change the signal. They're trying to understand if we can improve soil health by removing the conventional practices such as tilling. Tilling is labouring, you break the soil to air the soil. Right? If you break the soil to air the soil, you open pathway for fluids, the water comes in and leaves. It does not retain water. Or it also degrades the soil properties, contributes to erosion, it requires fertilizer, and you just keep cycling like this and making the soil worse and worse. In the United States, tilling has really destroyed the topsoil layer in the Midwest, and so it's been a huge problem for agriculture. The United States uses fertilizers and pesticides like crazy. You want to eat organic food there, literally. So there's a move called the regenerative agriculture, which is actually trying to reconstruct. It's not organic in the sense of chemical, it's actually rebuilding the soil for its mechanical properties. And so it's old practice, it's about composting, no-tilling, crop cover, crop rotation, and you can read about this or not. And so where does seismology stand? So I call that AGODAS. And because there's always good acronyms with that, come with something. So Ethan and I, we deployed. This is baby Catherine. She was under 2, so free on the flight. And we put out the DAS array all around. We did our best. This is a bouldering pad to damp the generator signal because we actually needed power there. That field, we didn't get good data from this one, but that's part of the experiment. This is the DAS cable we used. It's above the ground. It's recording seismic wave despite being above the ground. I think the little herb is coupling it. And so what we're trying to develop is this DAS for regenerative agriculture where we don't impact the soil at all. It's minimal for perturbation of the soil. We're just deploying on top. And it could be a rapid way to estimate permeability. So back to this field in particular, this is in the university. They're doing 4 meter by 4 meter different treatments. They're doing, they're controlling from compaction. They're controlling for different tilling depth, and then they're putting stuff that we eat. I don't quite know. I'll go quickly. So what we did is we deployed the DAS, and then we did a time dependence in this autocorrelation. So this is a 1D seismometer. So these are the 0 lag increasing in time. This is 36 hours. That's one of the channels at 30 hertz. And you can see the autocorrelation ringing a lot, but lots of fluctuations in time. And you see very different things right next to your channel. So I can skip that, but Florent, I think you study that. Florent, forgot where you are. But we turn these DAS signals into a rain meter gauge measurements, and then we measured seismic velocity shown in that heat map, and then this is the relative humidity measurement that was measured nearby. Lots of changes there. There's a lot of rain that happened halfway in the day, and this change is potentially due to drainage of the relative humidity. And we see a lot of variability, and this is in part because the seismic velocity in blue and the attenuation is varying a lot along the field in space, and is highly correlated with the type of tilling and compaction that the ecologists or the farmers have been using. So I will conclude quickly that to do this work correctly, I'm learning along the way, but we really need non-stationary and be careful about these non-stationary and localized node sources because they will affect our measurement. This is not news, but it's important to do that right. We see very small changes in seismic velocity. It's very small. That means that what's at depth is much greater. And there's just so much opportunities to explore temporal involution in tectonic, volcanic, hydrological systems, and it's really fun. So I think this is one of the greatest potential for pushing seismology outside of seismology. Okay, so I have something like 20 more slides, but I'll stop here. Yeah, I mean, what you're seeing here, this fluctuation, this is space, this is tilling, this is soil type. And you see the DV is going to change a lot just because of the soil type. So in predicting moisture, we have not done that yet. However, because we have this calibration effort, we can just create a calibration. It has to be informed somewhat by the soil type. So in the future, what needs to happen is combine like kind of geospatial analysis on the types of soil, the sensitivities, and in situ measurements, if possible, to really calibrate all of that. But I totally agree that this should be part of the calibration. Thank you.
It's nice for one place, but not
So hard to generalize. I agree. Yeah.
just staying on this, to predict the soil moisture, you have to take into account the temperature. It will affect
Yeah.
the soil.
But I think that's why I totally agree. That's why we need to account for it. And I don't quite know yet of the functional form that best accounts for these temperature effects. But in predicting soil moisture, we use DV. I think we can also use attenuation and these other factors that will influence it. But they have to be coupled somehow, because if the soil is very wet, it will be an instrument to propagating temperature changes at depth.
So the temperature has multiple effects. One is the direct, what triggered my comment was to say soil moisture directly affected by temperature. Now the temperature will also do other things that could produce strain that will affect now the fluids also.
Yeah.
So I'm just saying, you're starting
Two-way coupling.
this is a coupled problem.
We just need better models.
So can you go back to your curve in California and also
Parkfield?
Parkfield, but the second one,
The water.
the water? Yeah. What is here interesting is you have actually increase of seismic velocity to the pre-2004 level here that you explained by precipitation. Yes. Can this effect be also part of what you observe in Parkfield? Because I imagine this precipitation is statewide maybe phenomenon.
So thank you. The time series. So you look at this blue time series and then compare with Parkfield, which was actually shown as a cartoon. I'll I'll find it. There's huge variability in weather pattern in California. This is Parkfield. This is actually the precip from Parkfield. So 2004 is over here. It rains a lot in the northern part, but the greater variability increases with the south. It gets more extreme, like their culture. But it's much more local there.
So staying at Parkfield and making a connection to Florence, though, you explained the increasing velocities at Parkfield, you said compression.
Mm-hmm.
But could it be reduced by the creep? Ongoing creep north of where you're measuring is loading. Could it be creep rather than compression?
Yeah, so we looked at yes, we looked at the compression from geodetic measurements. So it could combine the loading of the creep plus the tectonic loading. I guess what we didn't differentiate, these are geodesically defined aerial strain. And so these correlations we're making were from that, so maybe there's combination, but we did not delve too much into the origin of these. And so yeah, maybe we didn't even calculate whether or not these compressions make sense purely with the interseismic loading versus a combination of the two.
To continue on Parkfield, it seems on your time series that the velocity increase is rather transient.
Yes, oops, sorry, this is the bonus. If you want to do DAS on glaciers, talk to me. Parkfield, yeah. So this jump here, the MWCS did not see it much. So we did not want to interpret it. There was an increase in low frequency tremor activity around then, but because I think it's the moving window cross spectrum, it's a way to do the phase lag measurements different than stretching. That one is more local and this one is very global. Stretching is very sensitive to kind of like all of the phase lags in the CODA wave we use. I suspect that there's some scattered wave late in the CODA that seems to be pushing the stretching in that direction that may be down-weighted in the inversion of the MWCS.
But then if you skip a cycle in 2014, then you keep the same load because it's flat, no?
Well, there's a weak trend in the MWCS. It's a weaker trend with less of a jump. We didn't interpret, this is increasing the number of parameters in the model that would be needed. So from the AIC perspective, we just kept a slope instead of adding a step and but definitely more work to do. Mm-hmm.
And then you write this equation up that has all these different natural phenomena.
Mm-hmm.
But is it true that, like, I would think there's some bias introduced here because we neglect this, and that the sensitivity of these different phenomena are not the same, but we assume that they are.
Yes, good point. So that's the so it's like this spatial and depth dependence on dV and dt that is not mapped correctly if we were to do that linear superposition without accounting for these sensitivities as well.
Yeah, and so since we don't ever account for that, and you could even think like
Yeah.
layered structure would be better than homogeneous, which is
Yep.
now, you can't generalize your equation. Or every time you go to
Yep.
some you have to refine these coefficients because you didn't take into account the structure.
It's a very good point. Another addition to that is I think the thermoelastic strain is going to look very different depending on the lithology, and the hydrological load is going to look spatial and more different as well. And so all of these assume a layered, flat, uniform effect everywhere. I think we need better Earth model. By that I mean like rock types, permeability structure, to better understand the spatial aspect and the sensitivity kernels as well. Okay, but because I do have a lot of bonus points, so find me this week. What do you want to talk about? I teach a lot. We teach a lot about coding. We have this cool experiment. It's not us, but Adam Booth deployed a vertical DAS on Greenland, and we did cool seismic velocity and wiggles. So find me and let's talk. Thank you. Thank you.